All right, so I'm here to talk to you about these ionic compounds. I got some learning targets up for us. The first one, number 15 of this unit, is going to be I can draw Lewis dot structures for an element. We've already drawn Lewis structures for covalent compounds, and it worked out pretty well, not too terrible. If you got the rules down, you can do it. But Lewis structures can also be Lewis dot structures, and the dots represent electrons. So that'll be really useful for us when representing ionic compounds and how they form bonds and what kind of charges they will get. So we need to talk about these Lewis dot structures for elements. You'll also be able to identify the charge of an element based off of the periodic table and drawing these Lewis dot structures for ionic compounds. So you can draw them for individual elements, and you can also put that together with other individual elements to make a ionic compound. Finally, in a future one, well, actually a little bit in this one, but more so in a future video, we will talk about writing the formula for a ionic compound. And we also talk about how to write the names of the ionic compounds containing both or all three things, a type 1 metal, a type 2 metal, and a polyatomic ion. And we'll also talk about what those polyatomic ions are, what a type 1 and a type 2 metal are, although you should be kind of familiar with what the PAIs are because you should have just finished up a quiz. So let's go on to the next page where I have two elements written, magnesium and oxygen, and we know that magnesium is a metal because it lies to the left of the metalloid staircase. Oxygen is a nonmetal. We also know that oxygen and magnesium are both going to be either very electronegative like oxygen is, or very not electronegative like magnesium is. And you take those differences in electronegativities between those two elements, you should notice that this falls into the greater than 1.6 range. So this will form an ionic compound. And when I draw a Lewis dot structure, I need to figure out how many valence electrons a neutral magnesium will have. So I'm going to write my symbol for magnesium, which is Mg, and I know that magnesium will have 2 valence electrons. But the question is, how would I know that magnesium or any other element would have a certain number of valence electrons? If we go to our periodic table, we can locate magnesium right over here. We can see that it is in the second column, and that is what tells us it's going to be, it's going to have 2 different valence electrons around it. Now, it is in the s block, it is the third row, so this would be a 3s orbital, and it will have 2 electrons, right? 1, 2 electrons in that 3s orbital. So those will be the valence electrons that we are representing on that magnesium that I drew. On the other side of the periodic table, we would have some other things happening, like say fluorine would have 7. And I know it has 7 because it is 1, 2. So we have 1, 2. I jump across my D block. I ignore those. 2, 13. So that's 3. 14 has a 4 in it. 15 has a 5. 16 has a 6. And 17 has a 7. So fluorine will have 7 valence electrons in it. Oxygen will have 6. Nitrogen will have 5, carbon 4, and I'm sure you can see the pattern from there. These valence electrons are something that we need to use to kind of figure out what kind of ions these things will form and how they will form a ionic compound. So oxygen, as I said before, is, well, let's go back to the periodic table. Oxygen is in this 6th column, or 16th column, I should say, but there's a 6 in that 16, right? So it will have 6 valence electrons. It wants to have those 6, or as a neutral element, it will have 6 valence electrons. Now, if I represent oxygen with its symbol O, I can draw 1, 2, 3, 4, 5, 6 electrons. And I am pairing them up as lone pairs, right? Just like I normally did with my, remember you had excess electrons, so you stuck them as lone pairs around the central, or when you were trying to assign all of your electrons that you counted from your covalent compound, you had to put a bunch of valence electrons around fluorine around the outside. These are the same type of deal that we're doing. If you look at the oxygen, you might notice that there's one side that doesn't have any at all electrons on it. And I've drawn it facing the magnesium, and there's a reason for that. But if I think about that side that's missing electrons, we can think it's missing 2 electrons. So there's spots for 2 electrons on that oxygen. And what's going to happen for our magnesium and our oxygen is that the electronegative oxygen, very electronegative oxygen, is going to grab those electrons off of the magnesium and put them in those empty spots. So I've drawn these 2 curved arrows to show where those electrons are coming from, the magnesium, and where they are going, to the oxygen. So curved arrows show the direction of a electrons movement from one element to another. Then I will draw another arrow, and this arrow, I kind of discussed this in class as well, says before is to the left side and after is to the right side. So before this reaction or whatever is going on here happens, we had a neutral magnesium with 2 valence electrons, and we had a neutral oxygen with 6 valence electrons. Then something happens, right? So our arrow means something happens. And after that something happens, we will have a new situation over here, which we'll kind of figure out what happens. Okay, so if I do this correctly, I will have a magnesium now, and it has no more valence electron or no more electrons in that former valence shell. It still has electrons, right? They're still there, but they're just 2s electrons. And so we'll just say that the 3s net is now empty, and magnesium has no more electrons in that 3s orbital. Oxygen, however, will have a 2p orbital, and it will have now all 8 of those electrons spots filled. And so oxygen has that octet. Remember, we had that octet that we have to follow. All of the elements in our S blocks and our P blocks will follow this octet rule. So if I look back to my periodic table, I will let's say, in a teal color, I will circle or box in my S block orbitals. And in green, I will box in the P block orbitals. Right, so, messed that up, didn't I? So there, in green, is P block, and blue is the S block. And you can kind of think that the helium should be over there, right next door to the hydrogen, and that whole block will now have the same height for every column. When we do that, that means that this block over here, the P block, is also going to have the same height for every column. So I'm going to get rid of this stuff just for make it easier. Okay, so oxygen will have 6 valence electrons. It becomes a -2 ion. And the reason why it becomes a -2 ion is because before, right, remember the arrow meant before is to the left. Before, it had 6 valence electrons. After, it has 8 valence electrons, a full outer octet. But that it was neutral with 6, and it gained 2 more electrons. Each electron has a -1 charge. This is now a -2 oxygen. So I'll put the charge on this oxygen as a 2-. Magnesium was neutral as well. It had 2 electrons in its valence shell, and now it's left all of its electrons out of its 3s orbital. But when we do that, when we get rid of all those electrons in that 3s orbital, that means that we now have an outer orbital of 2p, which is completely full. So the magnesium also has a stable outer octet, but we're not representing that because it lost electrons. When it loses those 2 electrons, it loses 2 negative charges. And when it was neutral before, losing 2 negative charges is the same thing as gaining 2 positive charges. So our magnesium becomes a +2, and our oxygen is now a -2. As it turns out, we would call this thing magnesium oxide. And unlike our covalent compounds, we do not have a prefix. We never have a prefix when it comes to our ionic compounds. There's a reason for that, and it has to do with these charges, and you'll see it come up here in just a little bit. But if I want to write this as a formula, the correct formula would be Mg for magnesium and O for oxygen. And why is there 1-to-1 ratio? Well, if you look at it, when I do this whole thing, all it takes is 1 magnesium to lose its electrons to an oxygen, and both of them are now happy with a full outer octet. So what we're looking for is some way to arrange a certain number of each metal and each nonmetal to make a neutral element in a neutral ionic compound where every element has a full outer octet. So you saw this when we did those note packets last time. Let's go back to the magnesium bromide example that we also saw last time. Once again, I will draw my magnesium. I will have 2 electrons around it, and then I will also draw my bromine, Br. Bromine will have 7 electrons. Once again, how do I know bromine has 7 electrons? Going back to our periodic table, I find bromine right down here, right next to krypton, and I know fluorine already has 7 electrons around it, but maybe you don't know that. So let's think about our magnesium real quick. We'll see magnesium is in the second column right up here, 2, right? Which means 2 outer electrons, 2 valence electrons. Boron will have 3 valence electrons. But if you look at this, there's not a 3, it's a 13, but there's still a 3 in it, right? Carbon has 14 above it in that column, and so it will have 4 valence electrons. Nitrogen has 15, it will have 5 valence electrons, so forth and so on, all the way up to like neon and helium, well, neon at least, which will have 8 valence electrons, and already as a neutral element will be a full outer octet. That is why we call them noble gases. They are very stable and they do not like to form bonds if they can possibly avoid it. So bromine, in this column with a 17 that has a 7 in it, will have 7 valence electrons. Oxygen, in all of its column buddies, it will have a 6 valence electrons. Nitrogen, phosphorus, they will have 5. Carbon will have 4. Boron is 3. All right, so bromine with its 7 valence electrons, magnesium will have 2 valence electrons. So if I draw a curved arrow to show where the first electron goes, it will go right here into that bromine's spot that it has open for an electron. But now I have a bromine that has a full outer octet. It will not want to accept or lose any of those electrons, and it will have a -1 charge on it. The thing is, our magnesium does not have a valence electron, does not have a full outer octet. So what we needed last time we talked about this was a second bromine. So here's my second bromine with 1, 2, 3, 4, 5, 6, and 7 valence electrons. The other electron from our magnesium will then get pulled by that bromine onto it, into that empty spot where it can accept that electron. And now I will have 2 bromines that will end up with a 1- charge, and I'll have this magnesium, only one of them, and it will have a 2+ charge. So if I look at these charges, and I count the number of positives, there's going to be a +2 from our magnesium, and then there will be, from our bromine, 2 bromines, each with a -1 charge. And so what we have is a +2 charge and a -2 charge from our bromines. Overall, that gives us 0. We want to be forming neutral compounds that have 8 electrons around every element. And this is what we've done. So this right here, we would call it MgBr2. And so if we go to name it and we think about our old naming convention, we might be tempted to call that magnesium dibromide. Unfortunately, that is not correct because we don't need to worry about prefixes in this new world of ionic bonding. We would just call this magnesium bromide, and that's it. We will talk about why that is again in the future. So magnesium bromide is always going to be MgBr2. There is no other way to make magnesium bromide. There's unlike, say, iron oxide. There could be about 3 or 4, maybe even 5 different iron oxides, but magnesium bromide, that can't happen. And the reason why is because magnesium is what we call a type 1 metal. Last thing that I want to talk about before I move on to discussing these type 1 versus type 2 metals is magnesium and a nitrogen. So we've already talked about the number of valence electrons around nitrogen. It has that 15 above it, so that means there's going to be 5 valence electrons. And magnesium, again, already has those 2. Pretty well known to us at this point. So if I draw my magnesium, again, it looks like this, and I'll draw my nitrogen with its 1, 2, 3, 4, 5 valence electrons. Nitrogen has 5 valence electrons, so it has a spot for 3 additional electrons. And this first thing that will happen is this nitrogen is going to start grabbing electrons and pulling them off of that magnesium. So it takes 1, 2. And now magnesium has no more to give because it is with a full outer octet. So we'll have a +2 magnesium. Those electrons will go into 2 of those spots on the nitrogen, but the nitrogen is still missing another electron, right? It needs to have a full outer octet, a configuration that's similar to a noble gas, but that's not what it has. If it pulls 2 off of magnesium, it has a configuration similar to a halogen gas like fluorine, bromine, or iodine, or chlorine. So since we're lacking that one electron that the nitrogen needs, we're going to need another magnesium. So we'll draw our second magnesium with 2 dots on it for 2 electrons, and that nitrogen will grab one of those 2 electrons and bring it over to itself. Now our nitrogen is full. That's great, but magnesium still has that dot down there that we need to deal with, because every one of these elements has to have a full outer octet, and overall this whole thing has to be a neutral compound. So we'll get another nitrogen this time. 1, 2, 3, 4, 5 electrons. Again, nitrogen still has those 3 spots for it, but there's only 1 electron around the magnesium. So we pull that electron onto our magnesium, making off of the magnesium onto the nitrogen is where that electron will go, making magnesium now a 2+ charge. So both of them are 2+, like we expect. But the nitrogen, it is still missing 2 spots. So now that we've done this, you might think, hey, magnesium has 2 electrons. We need a 3rd magnesium, and you would be correct. Here's my 3rd magnesium. I take the magnesiums and I put them on the nitrogen. So magnesium's electrons get pulled off of it and taken by the nitrogen. So now magnesium is a 2+. It has a full outer octet. And this nitrogen over on the right side, it has a -3 charge, a 3- charge. And it also, both of them, will have a stable outer octet. So there we go. We have everybody is an ion. Everybody is with a stable outer octet. And this whole thing here is actually neutral. And we can check that. So I have magnesium, each with a +2 charge. And there are 1, 2, 3 magnesiums. So that means I will take 3 times a +2, and I will get a +6 charge from all of our magnesiums. On the other side of things, we will have 1, 2 nitrogens, and those nitrogens each have a -3 charge. So for our nitrogens, we will add these 2 charges together, the magnesium and nitrogen, but the nitrogen's charge is going to be 2 nitrogens times -3 charges per nitrogen. What that gives us is a +6 charge from our magnesiums and a -6 charge from our nitrogens. Overall, that compound will be neutral. So everything has this full outer octet, everything is an ion, and the whole thing here is completely neutral. That is what we're looking for to form a full ionic compound. This thing, if we want to write the chemical symbol for it, would be Mg3N2. And then to name it, we would just call it magnesium nitride with a D. Remember, if it has a T, that means there's oxygens there, and we call that a polyatomic ion, either nitrate or nitrite. But nitride with a D is a single nitrogen, or is a nitrogen element by itself. It does not have oxygens on it. It is not a polyatomic ion. Again, there's no prefixes because there's no other way to arrange a certain number of magnesiums and a certain number of nitrogens to make a stable outer octet for everybody and to make a neutral compound. So this is what we have, Mg3N2, and this is our goal basically. But there's a little bit of an issue. This took like a long time to do, right? We had to draw all this stuff. We had to push all these electrons off of the magnesium onto the nitrogen. Is there a shortcut? Yes, there is. And it's actually pretty easy. This is called the crisscrossing method. So all I need to do is I just need to draw a single magnesium. I don't even need to draw my electrons. I'm not going to draw any arrows, nothing like that. So my magnesium will be a 2+ charge. And I also write out my nitrogen, which has a 3- charge. Crisscrossing says take the nitrogens, the number, not the negative sign. We don't have negative magnesiums or negative elements. We take that number and we put it down below magnesium. And then same thing with magnesium's number 2, I will put that down below nitrogen. What I get then is Mg, the 3 went with my magnesium, so we'll call it Mg3, and then the 2 went with our nitrogen, Mg3N2, which is exactly what we got up here. So that is a quick, easy way to see how to develop our ionic compound formulas. The name can just come from there. However, there's a little bit of a issue that happens when we have those D block metals. Things get kind of weird when they have multiple charges, and we have to deal with that. So let's talk about how we can look. Well, actually, no. Let's go back to our magnesium and our bromine, MgBr2. So again, I know magnesium has a +2 charge. I know the bromine has a 1- charge. Sorry, it should be is it 2+ or +2? I don't know. Some people get really sticklerly about this plus and minus sign. It has to be to the right. I personally don't care. I don't think it's that big of a deal. It means basically the same thing, but if you go to college for chemistry, they will get kind of on you about it. It needs to be 2+, not +2. So magnesium is 2+, bromine is 1-, and these two things, if we crisscross them, the 2 will go with our bromine, the 1 goes with our magnesium, and overall we will get an Mg1, right? We don't write ones though. So Mg1Br2, magnesium bromide. There we are. Does that work for everything that we've done so far? It certainly does. Let's look at magnesium oxide. So Mg with a plus or a 2+ charge, and oxygen with a 2-. So 2 goes with oxygen, 2 goes with magnesium, and what I would get them is Mg2O2. Oh, wait a minute. I said earlier that the correct term, or the correct way of writing magnesium oxide's formula is MgO, not Mg2O2. So what's going on here? We have a problem with this, sort of, maybe. When we form these ionic compounds, it acts like a chain event. And so what's going to happen is these magnesiums and these oxygens, they're going to start stacking up onto each other as quickly as they can in a certain pattern. So magnesium will go here with a 2+ charge, and next door to it will be an oxygen with a 2- charge. Also on the other side will be another 2- oxygen. And below the magnesium will be another 2-, and above the magnesium will be another 2- oxygen. All right, well, that's great, but this whole compound here is not neutral. So I need some more magnesiums. So I'll put an Mg2 up here, another Mg2 over here, and an Mg2 up here, and an Mg2 up here. And it's going to just keep chaining this whole situation until it runs out of the ability to add more magnesiums and oxygens. Maybe we run out of something. Maybe the energy that was helping it form goes away, like it cools off or something. But what the result is this compound that has a bunch of these things stacked together. And this is very different from something like our friend methane, or carbon tetrahydride, CH4. Methane, if it's stuck with other methanes, it's going to still be a methane, a carbon and 4 hydrogens bonded together. It will still be one packet of matter, but I can pull it apart from the other methanes pretty easily. Here, I cannot really just pull this apart. There's no real space between our magnesiums and our oxygens. There's nothing to get them apart from. And so they are basically just one continuous object that has all these magnesiums and oxygens alternating. So when we talk about a chemical formula for an ionic compound, as it turns out, ionic compounds do not form molecules. This right here is a molecule, but an ionic thing does not make a single discrete packet of matter. So what we're looking for when we when we write our chemical formula is the lowest ratio of magnesiums to oxygens. And so if I look at this piece right here, I see 1 magnesium, 1 oxygen. This one here is 1 magnesium and 1 oxygen. Right here, 1 magnesium and 1 oxygen. This magnesium over here, it's missing a partner, so we'll give it a friend. And there we go. Magnesium to oxygen ratio is 1:1. Anytime I take a sample anywhere in this substance, I will find for every 1 magnesium, there is exactly 1 oxygen. So our lowest ratio here is going to be 1:1. And another way to think about this is I have a 2 and I have a 2. If I divide both of those by the same number, I will get 1s, right? So I could just do that and think it's MgO. So a ratio of 2:2, if I take 2 divided by 2, that's the same thing as 1 divided by 1, right? And that will equal 1. So our magnesium 2, or Mg2O2, is actually just MgO. So our compounds, or our formulas for ionic compounds, they will give you the ratio, the number of oxygens to magnesiums or magnesiums to oxygens. They do not tell us that this is what a molecule is. It's an individual thing. It's a discrete packet of matter. No, it is the ratio in this big, long structure. All right, let's see. I don't think there's anything else that we need to do here. So this will be pretty much the end of this video. A little bit longer than I anticipated. Sorry about that, but there's a lot to kind of cover here and talk about and kind of see how things are going to behave. So our Lewis structures, so each of these things here, these oxygen, this magnesium, these are the Lewis dot structures for magnesium and oxygen. And that is how you would draw a Lewis dot structure. If you draw it as a neutral oxygen, it will look like this. If you draw it as a ionic oxygen with a -2 charge, it will look like that. But it's not going to be always very clear what goes where. So we'll have to work on that and how to figure out some of these answers to other questions. In addition, when I brought those learning targets up, we have some other stuff about how they interact together and how they form an ionic compound. So how would I draw a Lewis structure for an ionic compound? A good example for that is going to be this MgBr2. So this is my starting point that I've already drawn. I'm going to go ahead and just like copy it. So I get this one. And I'm going to bring it down here below so I get a little bit of space to work with. There we go. Okay, so magnesium and bromine. This is what was happening. This is the before picture, right? So before, it's a magnesium and with 2 valence electrons and some bromines with 7 valence electrons. Then I draw my arrow that shows that these things were 2 different things. There were 1 magnesium, 2 bromines that were neutral, and now the magnesium has become an Mg2+, and we will also have 2 bromines. Now the bromines, as you remember, have taken the electrons to get a full negative, or sorry, a full outer octet and a negative charge. So this, we draw the bromines that have taken the electrons. They should have electrons around them. If the nonmetal or the polyatomic ion or something takes those electrons away, it will have all the electrons full. But that's the one that we're going to represent with electrons. Magnesium's losing electrons, so it's dropping down in energy level, or its valence electrons are now in a lower energy level because it lost the ones in the higher energy level. So since it lost them, we draw them without those lost electrons. And this would be a Lewis structure for magnesium bromide. All right, so with that said, I'm going to let you go, and I will have another video here shortly about some of these naming stuff and trying to figure out how to deal with this charge and what it means for our ionic compounds. So hope to see you there.